So hi, and welcome back to another Æther Physics. Today I wanted to talk about a question I got from a viewer. He asked why is there a spherical form around a vortex? Why is there a spherical form of pressure equilibrium around a vortex? I'm going to try and explain that today. When we're talking about these vortices, we're talking about an incompressible flow, incompressible potential flow to be exact. Yeah, what this means is the incompressible means that you can't compress the flow, so all particles inside the fluid are connecting. The particles in the fluid aren't separated, they're all touching each other, so you can't compress it anymore. And the potential flow means that it is an irrotational flow. That means that, again, there are vortices. These vortices are filled with vortex lines, and these vortex lines are particles stacked on top of each other with the same vorticity factor. The most simple form would be the unknot in knot theory. That's the first knot. The simplest way to explain this is saying that it is a donut shape, a ring vortex. And we're going to draw one on the board right now. The ring vortex would look from the side. We would see it like this. Have two rolling parts, and this is just a slice of the donut. You can imagine this, I'm just gonna draw it, being a little donut, as you can see. This will make it a little bit donut shaped. It's just a slice of the donut. As you can see, a slice of a donut has two circles, two rolling circles, and they roll in a different direction. The one rotates in a clockwise and the other in a counterclockwise rotation, which would make, for instance, the top part is going clockwise, and then the south part, the down part, would go counterclockwise, and so it rolls together. So whenever we're checking out one of these two poles, we can call this a plus, and we can call this the minus. It's plus rotation, minus rotation. Plus for the clockwise and minus for counterclockwise. These two poles both have their own pressure field around it because of their rotation. We're just going to check out one. So I'm going to grab the red color indicating it's a positive flow. And we know there is a symmetry on the x-axis here because they both have their own pressure field around it. If we would forget the minus for a second, we would say that, for instance, the pressure here, we would call that pressure equals 1, so positive pressure here. And at twice the distance, we would call this circle that we can draw around it here somewhere, we could call that pressure equals 0.5, half of the pressure. When we double that again, we get another circular part with pressure equals 0.25. As you can see, the pressure decreases over distance. The negative pole of this dipole, because we can call it a dipole because it has two different poles, the one is positive and the other is negative, would have somewhat the same circle around it, but not exactly the same circle as you can see because they touch. We're not yet there. So what's going to happen is that this pressure equals 0.5 would continue in a circular manner there. And the next one would go you see they touch each other, and the pressure of this positive circle at 0.25 is going to cross here. So as you can see, the pressures of both vortices, or both slices of the same vortex, we can call this a plus source and a sink and source, plus or minus. It's a doublet. Because of the fact that they are touching each other, they are called in superposition. So superposition is when a plus and a minus, sink and source, or clockwise, counterclockwise, rotational flow. Whenever they touch, we call them in superposition. So when they are in superposition, they roll in a direction. So these two, because there is a flow, a negative flow here and a negative flow there, this entire vortex rolls in that direction. I'm gonna erase this drawing. Okay, again, a x-axis. And on that axis, we draw again, but a little bit smaller, two circles. And again, one part is positive and the other part is negative. The flows around it, when we remember the first drawing we had about the pressure of each vortex, the net pressure of both, we would draw it a little bit like this. Yeah, that's about right. So that's the pressure that both parts of the rolling vortex create around itself. If we would draw streamlines of the flow, these lines would react somewhat like this. Damn man, I needed some concentration to draw this. And so this rolling vortex that we just drew before, going in the left direction, would create a curvature on the original streamlines that were in the fluid before we considered it even inside the fluid. So this would eventually create a circle around it where we can say that the pressure equals 0. It's the equality of pressure of what this is trying to expand and that trying to get back at its original shape, because its original shape will be straight lines. This idea would probably still hold when we have knotted vortices, so not the simple donut-shaped vortex, a slice of the donut shape, but with, for instance, the trefoil knot, or the 5-fold knot, or the 9-fold knot, or 7-fold. There are so many knots that you can make from one vortex. Yeah, you can make a gazillion different knots. I don't know gazillion, but a lot. I think that this will be all for today. Thanks a lot for watching. If you have any questions or suggestions, you can leave them in the comment section below. I hope this explains a little bit more about this spherical equilibrium of pressure around a vortex. So, see you next time.